Unit 7, Exponents and Logarithms, Subsection 4, Applications. So there's three main things you're going to be able to do after this part. You're going to be able to illustrate how exponential and logarithmic functions may be used to model certain natural problems involving growth, decay, and return to equilibrium. Okay, you'll be able to relate natural growth, natural decay, and return to equilibrium to differential equations, or to the differential equations y prime equals ky, or y prime equals ky minus y0. And you're going to be able to fit exponential models to observed data for compound interest. So three main things for you to do this section, and let's get started. Part 1, exponential growth and decay. In many of the sciences, certain quantities grow or decay at a rate that is proportional to their size. In this section, we're going to model some of these quantities as exponential functions. So let's set the stage a little bit. If y equals f of t is the value of a quantity of y at any time t, and if the rate of change of y, now remember the rate of change is just y prime or dy dx, okay, or dy dt, with respect to time is proportional to its size, then we get these two little formulas here. So dy dt equals ky. Okay, and k is some kind of a constant. And we're going to have to solve that constant pretty much every formula. It's not a problem. It's actually quite easy. Okay, if k is bigger than 0, the equation above is called the law of natural growth. Okay, so k is bigger, the function's getting bigger, we're growing. Okay, if k is less than 0, then it's called the law of natural decay. So if this k is less than 0, our y value would be decreasing. Okay, not a big deal. All right, the solution to the equation dy dt equals ky is given by this. Now, funny, that formula is actually called an antiderivative, which we don't learn about till next unit. So for now, just trust me that that is the solution. That's how we're going to figure out all this stuff. And the only extra thing you need to know is that y0 is the initial value of the y. Okay, awesome. So let's start with exponential growth. If y equals ft is the number of individuals in a population of animals or bacteria cells, anything that grows exponentially, then it seems reasonable to expect that the growth rate f prime of t is proportional to the population. Words, words, words. I know it's a lot to take in. In a bacteria culture, the growth rate is a result of division of the bacteria, and the more bacteria that are present at any given moment, the greater the opportunity for them to grow. This reasoning is valid under ideal conditions of adequate food, freedom from disease, and unlimited room for growth. Okay, we have to make these assumptions in order for the equations to work. If the above conditions are met, then the size of the population at any time can be modeled by this crazy little equation. So y equals y0 e to the kt. Example 1. A bacteria culture starts with 2,000 bacteria, and after 3 hours, there are an estimated count of 10,000. Find the number of bacteria after t hours. So that's that equation up there, and we are just going to solve for the k value. Now, I warned you about that earlier. So the solving the k value, we're going to put in everything that we know. So y is 10,000. Sorry. So 10,000. Y0, we started with 2,000. So e to the k, and we know that it's been 3 hours. Okay, awesome. So you see, there's only one variable there. So let's solve for it. So divide by 2,000, divide by 2,000. So 5 equals e, and times, we're going to put the 3 in front, so times 3k. All right, we take the ln of both sides. So ln 5 equals ln e of the 3k. So that 3k pops down in front. So ln 5 equals 3k. Now remember that ln e, that is one of those logarithmic identities. So really this just cancels out and equals 1. So 3k times 1 is just 3k. So of course we can divide by 3, and k equals ln 5 over 3. So now getting the formula, so y equals, okay, we start with 2,000, e, then k we said was ln 5 over 3 times time. Now, one more thing I want to show you here, because this is always going to happen as well. So this 3, I can write it like this. Y equals 2,000 e to the ln 5 times t over 3. I can move that 3 over to the t. Now, the reason I would want to do that is because look at this. E to the ln 5. That's the other of those logarithmic identities, and that just equals 5. So really this just becomes y equals 2,000 times 5 to the t over 3. That's really handy. So that whole e function just goes away, and then there is our formula. Okay, so find the number of bacteria after 2 hours. So y equals 2,000 times 5 to the 2 over 3. Okay, t is 2, so that's 2 over 3. And when you type that into your calculator, okay, because you're not going to do stuff like this in your head, it works out to 5,848 bacteria cells. Okay, find the growth rate after 2 hours. Remember the growth rate is just y prime. Okay, so if the formula we said was 2,005 5 to the t over 3, so taking the derivative of this, okay, not to worry. So the 2,000's a constant, so we don't have to worry about that. Now, 5 to the t over 3, that's like any base to the x. So the derivative of that is 5 to the t over 3 times, okay, we have to take the ln of the base, okay, and then chain rule the t over 3, which is just 1/3. Wow, that was heavy. Okay, so remember, the derivative of any base to the x is equal b to the x ln b. Okay, so that's the formula that I'm pulling there. So that's what I used for that. So the derivative of 5 to the t over 3 is 5 to the t over 3 ln 5, and then chain ruling out the t over 3. Okay, so that's that. So typing this in, so after 2 hours, so y prime of 2, okay, so 2,000 times 5 to the 2 over 3, ln 5 times 1/3, that is 3,137 bacteria per hour. So at that particular moment in time, the bacteria are growing that fast. Okay, and then when will the population reach 18,000? So 18,000 equals 2,000, 5 to the t over 3. Okay, so we divide by 2,000, and 9 equals 5 to the t over 3. So now we turn this back into logarithmic form, okay, to solve for stuff like this. So it's going to be log base 5 of 9 equals t over 3. So t is going to be 3 log base 5 of 9. And when you type that into your calculator, you get 4.1 hours. Okay, so that is exponential growth. Radioactive decay. Radioactive substances decompose by spontaneously emitting radiation. The rate of decay is proportional to the amount of substance that is not yet disintegrated. Therefore, if y equals f of t is the mass of the substance that remains at time t, we have dy dt equals ky, where k is a negative constant as the mass is decreasing. Okay, and we can use y equals y0 e to the kt to model this situation. The term half-life is used to describe the amount of time it takes for a radioactive substance to decay to half its original value. Example 2. The half-life of polonium-210 is 140 days, and the sample of this element is 300 milligrams. Find the mass that remains after t days. Okay, so if the half-life is 140 days, it means that when t equals 140, the mass is 150 milligrams, or half of the original. So what that can do for us is that gives us kind of our initial amounts. So if we're using y equals y0 ekt, okay, so the y is going to be 150 milligrams. We're starting with 300 e to the k, and we don't know what k is, that's what we're solving for, times 140. Okay, so we're trying to solve for k now. So divide by 300, divide by 300. So 1/2 equals e times to the 140k. So, no problem. So we take the ln of both sides. Ln half equals 140k ln e. Now remember that the 140k was the exponent on the e, so that popped down. And then ln e is just 1, so that part completely cancels. So we end up with dividing by 140 divided by 140, and k equals ln 1/2 times 140. So then our formula becomes y equals 300 e, and then k is ln 1/2 over 140 times t. Now we're going to do the same thing here that we did last time. We're going to move the 140 over to the t. So y equals 300 e to the ln half times t over 140. Now, the ln and the e, they cancel, leaving us with just 1/2. So this is y equals 300 1/2 to the t over 140. Okay, now that's starting to look more like the physics 30 and the math 30-1 formulas. Okay, anyways, find the mass after 50 days. So y equals 300 1/2 to the 50 over 140. And when you type that into your calculator, you end up with 234.2 milligrams. Okay, find the rate of decrease of the mass after 50 days. So again, that is just the derivative. Okay, so y prime equals. Okay, so the 300 just comes out in front because it's a constant. Okay, now the derivative of 1/2. Okay, so that is that whole b to the x thing. So b to the x ln b. Okay, so that's going to be 1/2 to the 50 over 140 ln, the 50, we can't use that yet. Okay, is that still a time? Okay, so 50 over 140 ln 1/2, and then we take the chain rule of the t over 140, and we just get 1 over 140. Okay, and when we type that into the equation, we end up with, or we figure out y prime at 50, okay, we end up with negative 1.16 milligrams per day. Awesome. Okay, and the last one, how long will the sample take to decay to a mass of 200 milligrams? So 200 equals 300, 1/2 to the t over 140. Okay, great, divided by 300, divided by 300. So really that's 2/3 equals 1/2 to the t over 140. So we take the ln of both sides. So ln of 2/3 equals t over 140 ln of 1/2. Remember that exponent just comes down right in front. Okay, no big deal. Now we divide by ln 1/2. So ln of 2/3 divided by ln of 1/2 equals t over 140. So of course the 140 multiplies up, and we end up with t equaling 82 days. Okay, please feel free to verify that on your calculator. But that is example 2, and that is the end of this part, and we will do compound interest next. Thanks, guys. Call me if you need anything.